So Bobby, we have looked at various aspects of sinusoidal AC,
Yeah, yes.
alternating current, voltages, currents, and so on. Right? Are there any other electrical quantities that we need to see?
So, we need power.
Yes, I think that's right. Actually, didn't you and Janakiraman start off right
Yeah,
at the
yeah,
beginning
we
of the
did,
previous course?
Yeah, we
with
did
power
some
and
experiment,
energy.
etc. that I remember. Yeah.
That's right. It's really important, right? Power
Yeah.
and energy are really important electrical quantities.
Correct.
So we should.
So, for DC we know
correct.
V into I.
Okay, so that's right. You're right. So maybe I'll just summarize that here.
Yeah.
So if I take a DC voltage and apply it to a resistor, so let us say the voltage is V, so the current is I, then the power is V times I.
Yeah.
Right? That's
Yeah.
what we know. And you have other forms also.
Yeah,
You
yeah.
can combine this with Ohm's law.
Correct.
Right?
Then we have V square by R also.
And I squared R.
Yeah.
There are three forms. You just combine Ohm's law with V times I.
Yeah.
Okay.
But it's not very obvious when we come to sine waves, I think.
Okay. So
What voltage I should use, I don't know.
that's true. So shall we just do it?
Yeah.
Okay.
We should try.
So we'll take the same example.
Yeah.
Resistor.
Yeah.
That's the easiest,
Yeah.
right?
Yeah.
So I'll take a resistance R and we'll apply a voltage
Vm sin omega.
Vm sin omega t.
Yeah.
Okay. Okay, so I'm going to apply a voltage Vm sin omega t, and there is a current
Im sin omega.
Im sin omega t.
Basically, Vm and Im, you are indicating those are the maximum values.
The
peak
maximum values, the peak values.
Peak values.
Correct? Or the amplitude of the sinusoid.
Yes.
Right? Okay, excellent. So the voltage is Vm sin omega t. Because it's a resistor, it will be in phase.
Yeah.
So the current peak value is Im. We are calling it Im sin omega t.
Yes.
Perfect.
So whatever we learned for DC should be valid for every instant of time in the case of, correct?
Makes sense.
Yeah.
Right?
Yeah.
Okay. So that means that what you are saying is
instantaneous power.
Instantaneous power. So
maybe small p.
So maybe small p. So let's write it like this. I'll call it P of t.
Yeah.
Right?
Yeah.
This is the instantaneous power.
Correct.
So instantaneous power should be V times I.
Yes.
Right? So Vm sin omega t times Im sin omega t.
Exactly. That should be correct.
Okay.
Maybe we can do, yeah.
Okay, so Vm sin omega t times Im sin omega t. We should simplify this.
Yeah, maybe we can rewrite sine square omega t.
Sine square omega t is what we need to rewrite, right?
Yeah.
Okay, so Vm times Im times sine squared. Okay, I think sine squared omega t, there is a relation to cos 2 omega t. And probably sine 2 omega t as well, but cos 2 omega t is probably easier to use.
Yeah.
So I'll write it as Vm times Im. So sine squared omega t is half of 1 minus cos 2 omega t. I think this is right.
Okay. So this means this instantaneous power will be at twice the frequency of.
Looks like it, right? We should plot it. Right? I think you are right.
Yeah.
Let's plot it to confirm that is correct.
Yeah.
We should check. So let's say we are plotting voltage or current.
Yeah.
Okay. So shall I say that the voltage we said is Vm sin omega t.
Yeah.
So this is Vm. Okay. So maybe I'll
some other color.
Other color is good. I'll use this color for Im sin omega t.
Yeah.
So maybe it's the same but different amplitude.
Yeah.
So this is Im sin omega t. And we're going to multiply the two.
Correct.
Okay.
Every instant.
Every instant. So Vm times Im. So the peak value will definitely be Vm times Im.
Exactly.
Right? That much we can tell. So I'll show that here.
Another color we will select.
Yes. Yeah. So I have chosen another color. Oops, sorry. I should be. So Vm times Im. So it looks like So Vm sin omega t times Im sin omega t. So it looks something like this.
Positive. Yeah.
But here after in the second half cycle,
both are negative. So
both are negative. Again, it will be positive. Oh, okay. So you will get something like this.
Yeah.
Oh, it will be symmetric actually.
Yeah.
It will be the exact same thing repeated.
Yes.
And in fact, this will go on, right?
Yeah.
So if I were to imagine this, it will go on like this.
So in one time period of input excitation,
you seem to be getting two periods of the power.
So this cos 2 omega t makes
sense, right?
Okay, nice.
So 2 periods of p of t. That's what you're saying.
Yeah.
And this makes a lot of sense then.
Yeah.
Right? Okay, great. Excellent. So, which means, so this is the instantaneous
power.
Okay.
Now, if you are using a heater or something, I'm not going to look at each instant what's the power.
Instant of time. Correct.
So I need to get some average value.
And we need to, so anyway, this sinusoid has some time period t, no?
Correct.
So this is some time period t, let us say. This starts from 0.
Yeah.
And it makes sense. After that, it's repeating.
Correct.
So we'll just average over this time period t.
One time period.
T. So then I'll call it P average. P average. So I need to integrate P of t and then divide it by the period.
Yeah.
Is correct?
Yeah.
Perfect. So 1 by t integral 0 to t P of t dt.
Correct.
And this is basically 1 by t integral 0 to t Vm half Vm Im into 1 minus cos 2 omega t dt.
Yeah.
Okay.
Anyway, this cos 2 omega t time will go to
I think that's
0.
right?
Yeah.
That seems like that.
Yeah.
So I'm just trying to write this in the same line to make it okay.
Yeah.
And clearly what you are saying is that this term will get integrated to 0.
Yeah, because it's a sine wave or cosine wave. Average value over a cycle is 0.
Yeah, in fact, you're averaging over 2 cycles.
Correct.
Because this is cos 2 omega t.
Correct.
And this t is, let's also write that down. This time period t, no? Is basically t is 2 pi over omega.
Correct.
So here, this you'll have 2 periods of cos 2 omega t.
Yeah.
Definitely it will get integrated to 0.
Yeah.
So which means only this portion will remain and dt will give you t. So this is actually the average power is basically Vm Im by 2. It seems like it's just half Vm Im. So this integral 1 dt will just give you t.
Correct.
Capital T,
correct,
right?
Correct.
Okay. Okay.
So maybe we can split and write also?
Split and write it equally. Okay. So I'll divide this 2 among these two.
Yeah.
Okay. So I have to do Vm by root 2 times Im by root 2.
This is very familiar
Yes. This is the RMS value.
Okay.
Because the peak value or the amplitude by root 2 gives you the RMS value
for the
sinusoid. Yes.
Okay.
So this is VRMS and this is IRMS.
Okay. So this is just RMS value of voltage multiplied by RMS value of current.
Correct.
In the case of resistance alone, resistive load
In the case of resistive loads. So it is just VRMS times IRMS. So in fact, this is like practically a definition, right? So the RMS, you take the product of the root mean squared values, you will get the power directly.
Okay.
And now I know we had written V squared by R, I squared R. All of those things will be valid.
Okay.
So we can write it as, because the relationship between VRMS and IRMS will also be this R, Ohm's law.
Yes.
Right? So VRMS squared by R, and that will also be equal to IRMS squared times R. So both these will be valid.
Hey, actually, this reminds me something. When we represent things in polar form, or when we have phasor representation, if we can actually represent in RMS,
seems like it will be a lot better for power calculations.
Correct.
Right?
Correct.
In fact, I think that's right. So most textbooks actually do that. They actually use phasors, especially because phasors are very useful when analyzing power circuits, right? Where you are very interested in power.
Yeah.
So it makes a lot of sense. So in fact, going forward, we should follow that convention.
Okay. Okay.
We'll just go forward saying that we'll use directly write the when we write it in polar form, the length of the phasor is the RMS value. We should just go forward using that.
So when you say V angle 0, that V is RMS value.
Is the RMS value. So that's what we should do. I think you're perfectly right. We should do this.
Okay.
So from now on, the convention we'll say is if you have a phasor of length V, or we write it as V angle 0, or same thing for current as well. If you have I or I angle 0, this means that RMS value. RMS values are V and I respectively. Which means we need to make a change in the way we write in the time domain. Okay. So which means we need to say time domain. Now we are saying V angle, this length is V, right? So when you write it as something sin omega t, we need to multiply by root 2.
Root 2.
That's right. So which means this voltage in the time domain will be root 2 V sin omega
sin omega t.
And this would be root 2I.
Okay.
Omega t.
So the Vm is root 2 V.
Vm is root 2 V, right? So this is Vm and this would be Im. The peak value is root 2 times the RMS value. So now going forward in this course, we will follow this convention where the phasor lengths are all the RMS values. Not the peak values. And in fact, that is commonly followed
in other textbooks
as well. So we should also follow the same convention.
Yeah.
Now that you have brought
I've
it up,
seen some textbooks, some textbooks follow peak value also.
That's right. There are some areas of electrical engineering where peak value is also important.
Yeah.
Right. So there are some textbooks which follow the peak value as well. We will follow the RMS value.
Anyway, we cannot use a mix of this.
You cannot use a mix of this. It will end in disaster for calculation.
In the sense, either it has to be RMS alone or peak alone.
That's right.
So here we will stick to RMS.
Here we will stick to RMS in this course.
Great. This is nice.
Yeah.
Now, see, resistor, maybe it is easy.
Yes.
If it's an impedance, is it just V into I or?
Okay. We should calculate it.
Okay.
Because we are doing some integration as well. We need to calculate it to be careful. We don't make any mistakes.
Because that phase is going to do something.
That phase is going to, because the minute you say this is an impedance, the current phasor and voltage phasor will no longer be in phase with each other. So, P of t may be different from what we expect.
So these equations are not going to take care of that.
They are not going to take care. We should be careful.
Let us
do it. Let us do it. So, what you are saying is,
I have an impedance, maybe Z angle minus phi or something.
Okay, Z angle minus phi. Okay, Z angle minus phi.
Yeah.
And this is your V angle 0.
Basically, the same Vm sin omega t.
The same Vm sin omega t. And so root 2 times V is Vm.
Yeah.
Right?
Correct.
We'll follow the same convention as we did here.
Correct.
Right? So Vm sin omega t. So I'll also write them here.
Yeah.
Root 2 times V is Vm.
Yeah.
Just for this example alone. Going forward after that, we'll just say it is this, right?
Yeah.
So which means the input sinusoid is Vm sin omega t.
Yes.
That's what we are saying.
Yeah.
Okay. So this is basically Vm sin omega t. And now the current is basically Im sin omega t then.
Im sin omega t and
but now there's an angle.
Yeah.
So let's do the phasor form first because it's easy.
Yeah.
Right? So which means, so before we write this, then this current, we'll write it as, so we said that you can do a direct division of the magnitudes.
Yes.
And a subtraction of the phasors.
Yeah.
Right?
Yeah.
So let us do that. So this current is going to be V by Z. So V by Z.
Angle phi.
Plus phi.
Yeah.
Right? 0 minus phi.
Yeah.
Angle phi.
Yeah.
Okay. That's the current in phasor form.
Yes.
Which means the actual time domain form, okay, will be root 2 times that.
Yes.
So root 2 V by Z angle phi.
Yeah.
Not angle phi, root 2 V by Z sine omega t plus phi.
Yes.
That's what we are saying.
So we will write it as maybe I equal to, just to avoid.
Correct. Yeah. Okay, yeah, you're right. So we'll just write it. Let me move this. So this is current.
Yeah.
This will avoid confusion.
Yes,
You're right.
yes,
We should
yeah,
do this.
yeah.
I equals V by Z angle phi.
Yeah.
And I
in time domain.
In time domain. So this is basically Im sin omega t.
Yeah.
That is equal to, from this,
Im sin omega t plus phi.
correct. So
Yeah.
plus phi.
Yeah.
So we'll just, so maybe we should be careful in how we write this. So RMS value is V by Z.
Yeah.
We'll do from first principles. RMS value is V by Z. Peak value is root 2 V by Z.
Yeah.
So root 2 V by Z. And this angle phi corresponds to the phase. So it will be omega t plus phi. Is this correct?
That's correct.
Perfect. So first principles, always you can't go wrong.
Yeah.
You have to follow every step.
Yeah.
Okay, great. So and so now the reason I wrote that was, this is Im,
Yes.
correct?
Yes.
And that happens to, correct. So you have that root 2 V by Z, that is Im.
Yeah.
Perfect.
Yeah.
Perfect. I think we have everything in place.
Correct.
So we have the voltage,
And current.
So now we can write P of t,
Yeah. The instantaneous power.
the instantaneous power. And we know from the previous course as well, P of t is always V of t times I of t.
Yeah.
Right? It's a product of voltage and current, will always give you the instantaneous power. So this V of t is Vm sin omega t. And I of t is
Im sin omega t plus
Im,
phi.
Im sin omega t plus phi.
So sin A,
Perfect.
sin B.
Sin A, sin B. So cos of A plus B is cos A cos B minus sin A sin B. So this would be Vm times Im. So sin A sin B would be half of cos of A minus B.
Yeah.
So cos phi
Yeah.
minus cos of A plus B. So
Yeah.
which would be cos of 2 omega t plus phi. Okay.
Yeah.
So now you have to integrate this, right? So now we will say P average
Again, integrate over a cycle.
over a cycle. So this would be 1 by t integral 0 to t P of t dt,
Yeah.
right? So now it should be straightforward to see that I'll just mark it here. This is a 2 omega t component. This should integrate to 0.
Yeah. After integration, it will go to 0.
Yes. So maybe shall we write it out explicitly?
Maybe.
Good idea. Let's not shortcut
Yeah.
take any shortcuts. So we should not say that this is 0. This is actually time varying.
Yeah.
So this would be, so 1 by t. So
Vm, Im, we can take outside maybe. Vm, Im.
Vm Im by 2.
2. Yeah.
So this would be integral 0 to t.
Yeah.
We can even take cos phi out.
Because that's also a constant.
That's also a constant.
Yeah.
Oh, maybe
It's correct only.
it's correct, right? So we'll integrate this portion.
Yeah.
So this would be cos phi.
Only, yeah.
So now into t, because we are integrating dt.
Yeah.
This would be t.
Yeah.
And the second portion would be Vm 1 by t Vm Im by 2 times integral of cos of 2 omega t plus phi. That would integrate to 0.
Yeah.
Right? That's what we are saying.
Exactly.
Perfect. Okay.
So TT will get cancelled.
TT will get cancelled. So this is actually giving you something different.
There is a new guy there.
Yes. This cos phi. Okay.
So it is VRMS because Vm by 2, Im by 2 is a.
That's true. Let's write it in that form. VRMS times IRMS times cos phi.
Oh.
That's right. Oh, interesting.
So
earlier we just got VRMS times IRMS for the resistor.
now there is a new factor.
That's a new factor. That's right. Oh, that's interesting.
Which is the cause of the angle between those two.
That's right. It's the cause of the angle between the current and the voltage. In fact, yes. So the current in this, the way we have drawn it, for positive phi, the current is actually leading the voltage.
Yeah.
Right? So, the actual power is actually related to the cosine of the angle between them.
Yeah.
Okay? So,
any name for this? It's a factor.
Yes, I know. It is a power factor,
Exactly.
mostly, right?
Exactly.
It must be called the power factor.
Yeah. Yeah.
Okay.
Yeah.
Great. So, looks like the power factor is, so looks like this average power is related to VRMS, IRMS cos phi. And
if it's a
normally this phi, no, because you said Z angle minus phi, it will always be either go from minus 90 degrees to plus 90 degrees.
Yeah.
Right? So, this cos phi will always be positive. Actually, that's what we expect, because the average power should always be positive.
Correct,
no?
correct.
It's not absorbing power.
Correct.
Perfect.
Correct.
So, that makes sense.
Correct.
Right? So,
Also, if it is just resistive load,
yes.
then phi is
0. Cos phi is 1.
Or then we get VRMS IRMS.
VRMS times IRMS. Perfect.
That means this equation takes care of
everything.
Resistive
The
case
most
also.
general case. That's right.
Okay.
So, this takes care of resistive, capacitive and inductive cases.
Okay.
All of them.
Okay.
Makes sense.
Should we see earlier when we did the experiment in the previous course, it was for the 230 volt.
Yes, that's right.
Yeah. So this will be root 2 230 sin omega t getting multiplied with some current.
That's right. Actually, that's right. So the what people say 230 volts that you are seeing in the power on the power points, that is actually the RMS value.
RMS value.
Because actually this is exactly what we discussed here. You are, in many cases, you are interested in the power.
Yeah.
So very often you just, that's why we said
use the RMS.
You just use the RMS, draw the phasor diagrams with RMS. You just, you can very easily calculate power. Because in power delivery systems, that's what you're interested in.
So when people say 230 volt, the peak value is root 2 times.
Root 2 times 230. So that's right. So if I take 230 volts, right? So this is the RMS value. So peak value is root 2 times 230.
Okay. Which is
1.4.
325 or something.
About 325. That's right. I think you're right. About 325 volts. Yes. So in fact, the students should not do it with their oscilloscope because it can't handle 230 volts.
Yeah.
But if you actually
only
take
some fumes will come out.
Only fumes will come out. But if you actually take an oscilloscope that can measure up to this power, you will actually be able to measure the sinusoidal voltage and the peak value as 325. So normally, in fact, if you look carefully at the multimeter, digital or analog multimeters, it will tell you whether you are measuring the RMS value.
Okay.
When you actually measure it.